Hi everyone, my name is Amit Gainis. I'm a security researcher, part of a penetration testing team at Argus Cybersecurity. And today I'm going to share with you this talk that is simply called Tales from a Penetration Testing Team. Our team receives and reverse engineers many ECUs from our clients, such as BCM, TCUs, instrument clusters, airbags, and other safety critical systems. We find zero-day vulnerabilities in all of them. Some are easy to exploit, some are harder. Some have very complex software bugs that could be easily missed by a developer, while others should have been caught during a standard security review. In this short talk, I'll present 3 distinct zero-day vulnerabilities found in 3 different OEMs using 3 diverse communication methods. These cases will illustrate both the complexity and variety of security issues encountered by our team in recent years. Vulnerability number 1 is an arbitrary remote code execution via CANFD network access. Our vulnerability starts, just like many other vulnerabilities, with a memcopy. And this memcopy copies our own 64 bytes of data to somewhere in memory. Let's call it some PTR. Well, it turns out that this some PTR points to a buffer whose size is 32 bytes, smaller than the copied data. So we have a very classic buffer overflow. Additionally, it turns out that the same some PTR is actually located after that overwritten buffer. This gives us a very powerful primitive. Since we are able to override the pointer, the next time the memcopy will take place, we will control its destination. If that's not enough, the entire vulnerable code is running as a part of an interrupt service routine. This means we are effectively running in supervisor mode and have few obstacles to get full control of the device. This vulnerability lets us use an arbitrary write primitive via CANFD messages, which we use to write directly to the return address on the stack. This bypassed stack analysis that were found in the system, as well as CFI that monitored forward edge function calls only. Then, by using return-oriented programming, we can rope our way to get arbitrary code execution. Vulnerability number 2. Our target in this case was the communication stack of an ECU connected to the in-vehicle Ethernet network. We used our interface fuzzing tool to fuzz both the SAM-IP service discovery protocol, a well-known automotive protocol, and the IPsec protocol. In both cases, our fuzzer successfully crashed the system. We analyzed the crash dump, and we saw that the stack overflow caused the program counter to point to an invalid memory area. Note that there were no stack canaries added to the vulnerable functions. In the IPsec task, we gained full control over the program counter, but this task only had limited permissions for the safety critical resources. In the SD task, we only had control over the 3 least significant bytes of the program counter. But in this case, the task had full permissions for the safety critical resources. The limit is rooted in the Ethernet MTU, which is 1500 bytes per frame. So, at a first glance, it seems that we can't bypass it. But there is a way to send more than 1500 bytes per frame, just not directly over the Ethernet interface. By using an internal socket, we can send up to 8 kilobytes of data. So, by using the IPsec task vulnerability to control its task, we can send a frame using an internal socket between the tasks, leading to full control over the SD task as well. By using the union of these 2 limited vulnerabilities, we can gain full control over the safety critical resources of this ECU. Vulnerability number 3 is a remote and persistent vulnerability via cellular connection. In this setup, we had a TCU with a modem connected to a safety critical CAN bus. The TCU communicates with the backend via secure TLS connection and can also receive a binary SMS to trigger communication with the backend. Zooming into the implementation, the TCU has a TLS client for the authenticated TLS session and an SMS client for the unauthenticated SMS messages. These clients forward messages to the message parcel module. type A messages from the SMS and type B from the TLS. At this point, you can probably guess what an attacker can do. An attacker can send type B messages via binary SMS, and the parser doesn't distinguish between the channels. So we had a nice secure TLS gate, but also an SMS channel to bypass it. Exploiting this vulnerability, we were able to replace a file in the system, and that enabled us to run a full demo of injecting CAN messages from our location in Tel Aviv, Israel, to impact the vehicle located in Europe. Our penetration test demonstrates that high-severity zero-day vulnerabilities are still common in multiple types of ECUs. Some are safety-critical. These vulnerabilities are the result of faulty implementations of interfaces and protocols, exploitable via CAN, Ethernet, or cellular connection. So, how can you avoid similar vulnerabilities in the future? Here are a few takeaways. Augmented security awareness during the development process could have helped detect at least some of the issues we encountered. Deploying fuzzing tools in the early validation stages is an effective way to harvest the low-hanging security fruit. Hardening is crucial. Use stack canaries, CFI, properly configured MPUs, and ASLR whenever possible. Penetration tests based on labor-intensive manual code review should be planned after all the other validation steps to catch the more subtle faults that would otherwise be missed. Knowledge sharing across the industry will help us all learn from each other's insights and create a better and safer connected vehicles. Interested in learning more about vehicle penetration testing? Read the full paper Tales from a Penetration Testing Team.